there, ladies and gentlemen, boys and girls. Welcome to the Hartford Astronomy Group. Today we've got an extra special meeting where we've got Jack Martin, who's going to show us his spectroscopy work. I'm just going to hand it straight over to Jack. So Jack, the floor is yours.
Okay, good morning everybody. Welcome to the Huggins Spectroscopic Observatory live in Essex, and I'm going to give you a trip round the solar spectrum using a low-res spectrograph set at the highest possible resolution. And what I'll do is I'll start the show by showing you, we're going to move from the red right down to the blue end of the optical spectrum. So what you can actually see at the moment is the telluric lines from the Earth's atmosphere, and they're about 700 nanometers wavelength in the red near infrared part of the spectrum, and these are the tellurics all along here, and we have a graphical representation, a trace of the absorption lines. But just before I go into that, I just want to show you, give you an understanding of what it is we're actually looking at here and the core of all spectroscopy. So the dark absorption lines that I've just shown you are electron transitions, and they are created when an electron jumps from an energy level from E1 up to E2, a shell.
Can I interrupt you there, Jack? On my screen, I've just got a grey box.
Oh, right, okay. Yeah, I think I know what the issue is there. I'll come back to that later. But I'll just carry on now with this. So I'm going to start the imaging. It's set at 5 seconds in maxim DL. And what I'm going to do is move the micrometer on the spectrograph, which is just out of the picture here, and you'll see the spectrum move. Now, at the moment, it's cloudy, and I should emphasize that the spectrograph is pointed away from the sun. It's picking up the Rayleigh scattering off the Earth's atmosphere, off of the cloud. Although the sun is trying to come through, if this setup was pointed directly at the sun, it would burn out the sensor of the CCD camera. So it's pointing well away, and it works very well on cloudy days. Right. So let's start the journey through the spectrum. I'm just moving the the micrometer gauge, and you can see it's changing. I'm moving it down to the H alpha line. The optimum exposure seems to be set at 5 seconds at the moment, although I may have to change that to see how it settles down. Right, now I'm just gonna stop that for a moment just to see how that's looking. Just adjust that to 3 seconds, see if that makes it any better. Let's move it. Start again. We should be coming into the range of hydrogen alpha in a moment. Here we are. Bang on, this is the H alpha line. That's it, it's settled down now because it's totally dependent on sky conditions and turbulence and the atmospheric light. So with what we can see here, I'm just going to stop this. This is the H alpha line, 656 nanometers in the red end, and the hydrogen alpha line is a line that we use to look through our solar telescopes when we're looking at the sun. Some of you will have solar telescopes and will have done observations with an H alpha telescope. As you can see, it's a very dark, broad line. It's the strongest of the absorption lines of the sun. We see it. You'll notice the image looks a little bit curved. That's because it's a littrospectrograph design, and that is the nature of the optical train in a littrospectrograph, but it really doesn't matter because you're only looking at a section. So let's move on now. Next up is the sodium doublet. So we'll just start the process of winding the micrometer along. Fortunately, these lines are very distinct, and you can't really miss them. And that's quite a way down, and they are quite close together. Let's just stop it there and do an adjustment. Here we are, the sodium doublet. That's it, it's looking good. Just get that more centralized. So let's have a view of the graph. Here we are. So again, two dark absorption lines, and the graph. One is a darker absorption line than the other, as seen by the trace. This pair of lines are very close together. This one here is at 588 nanometers, and the one next to it is at 589 nanometers, about 1 or 2 nanometers apart, so that they are very close together and very easy to identify. Now we'll move on to the magnesium triplet, and we're heading down towards the green end of the spectrum now, where around about 500 nanometers, where the eye is the human eye is most sensitive. I found when I've given these demonstrations in the past, 3 seconds is usually the optimum exposure, but for some reason it's not giving the best image, and it seems to be taking a little while to settle down. Again, that would be to do with the Earth's atmosphere today. It's quite windy here as well. That may have something to do with it. So we should soon see 3 very distinct lines. Keep moving it. I think this is it here, yeah. Right. See if I can get that nice and central. There we go. Probably to do with the sensitivity of the chip in the CCD camera. It's more sensitive to certain parts of the spectra than others, but here we have it, the sodium doublet. I'll just centralize that up. I think we've got it. Let that take another image and just let that settle down. There we go. That's it. Right, now this looks interesting to me. I've got I'm looking at comparison spectra here on the chart. Now this magnesium triplet is quite interesting. It comes in at 516, 517 and 518 angstrom units. So it's there, 518, 517, 516. Now you can see this band here, the one at 516. You can see what appears to be a little bit of emission going on there. These are completely dark absorption lines, but there seems to be a little bit of emission. Now, I've not seen this before, and when you look, I'm looking at the chart now, and it's definitely not on the chart. It's appearing as a dark absorption line, so that's quite interesting. I don't know what is causing that to happen, and I've never seen it before. So if anybody knows the answer to that, please send me an email. Usually that 516 nanometer line is in absorption. It may be something to do with the adjustments in maxim DL, but I don't know. So we'll move on now. See if I can get you the hydrogen beta line. We'll start on this. And what I'm going to do actually is just stop the exposure a second and have another look at this this emissions feature here, or what appears to be an emission feature. I'm just going to try adjustment of the contrast here, and you should be able to see it's as if the line is split in two, right? That might be the Zeeman effect off the top of my head. I don't know, but I've not seen that before, and I hope you can see this very clearly. Okay, so we're gonna move on now, and we're gonna go and have a look at the hydrogen alpha line. Cancel that. Press the wrong button there. I'm sorry. View graph window again. So let's move on. Let's go and have a look at the H beta line, which is the second line of the hydrogen Balmer series, named after its discoverer. Discoverer Balmer. I think he was Swiss or German in, like, I don't know, the 1860s or thereabouts. Now, spotting the hydrogen beta line is not going to be very easy because it's weaker than the hydrogen alpha line, but I think we're there. But it's still very distinct. Yeah, that's it. That is the hydrogen beta line. Right, let's just center that up a little bit and get a good settled image. Right, there we are. So this is the H beta line. The hydrogen Balmer series goes down to about H33 or something like that. 33 Balmer absorption lines, and it is possible to observe them in A-type stars. For example, stars like Sirius, which contain the hydrogen Balmer lines. It's an A-type absorption line star, and it's a classic one, and it's also the brightest in the northern hemisphere. And under very high resolution, you can split the spectrum with a high resolution grating, and it is possible to see them. I've not seen it on the sun, probably because the resolution of this particular spectrograph isn't high enough. Now, the hydrogen Balmer line comes in at 486 nanometers. So we're looking now towards the blue end of the spectrum. We're coming into that, and that's where the sensitivity of the eye drops off, and it's not as broad as the hydrogen alpha line, which is the strongest of all the hydrogen Balmer series, but it is very distinctive. So let's move now down to the blue end, which is even more difficult for the eye and the spectrograph to see, because the sensitivity of the spectrograph drops off at the blue end, although you can see quite distinctly the calcium doublet. So let's see where we are at the moment. With this spectrograph can resolve 2,000 solar spectral lines with the highest resolution grating, which is what I'm using at the moment, the 2,400. So we're coming into the blue now, or the violet end of the electromagnetic of the solar spectrum. Right now, I think we're almost there. Yeah, looks like we're there. Just give that a moment to settle down. Center it a bit more, see if I can get a better, move it forward just to make sure. Yeah, there we go. That looks like it to me. Right. We're definitely on that now because the sensitivity's dropped right off down there. Right, so I'm just going to close this for a moment. This is what we're looking at here, this pair of lines. Right. I'm just going to view the graph, and we'll see it. Well, it doesn't look like it. See if I can get that more distinct. It doesn't look like we're quite there yet, because they should be much broader. There we are. Just center that up a little bit. See if I can improve the image. So these are two very dark, broad lines, the calcium K lines, they're known as the calcium K absorption lines. And just see if I can tweak that a little bit. that's as good as it's going to get. One thing about spectroscopy, everything is a compromise in spectroscopy. View, graph windows. Okay, that's as good as it will get. So what we're seeing here is the two broad calcium K lines, and this is 393 nanometers and 397 nanometers. So these two lines are 4 nanometers apart. So they're very almost as close, as, well, not as close together as the sodium doublet, but they're close and very distinctive. Now, a few years ago, Coronado brought out the calcium K PST telescope for looking at the sun in the calcium line. This line, this is the line that we're looking at, and it shows a different layer of the sun's atmosphere compared to hydrogen alpha. And I went down to Fulloscopes with a view to buying one of these telescopes, and I tested it, and all I could see was a violet disc and no detail at all. Someone else was down there and they had a look, and they could see white spots, and they could see quite a bit of detail. So that was quite interesting. But telescopes of that kind that operate in the calcium blue end of the spectrum really are imaging telescopes, unlike the H alpha. Right, so that concludes the tour of the solar spectrum. I just wanted to show you this core of spectroscopy. Can you see that, Alan? No? That's really odd. Move this window away from the shared application. I may have to come out of the setup, disconnect. I'm not going to save the image. Am I still sharing?
Yes, yeah.
It says screen sharing has stopped.
Restart. Well, put on your screen what it is you want to share with us, and then go back to the screen sharing. You've got control of it.
Right. I seem to have lost that image. No. Can you see it now?
Nothing at the moment.
I think, oh, that's really odd. Right, let's just. Can you see that?
No. When you go to screen sharing, does it not give you a little drop down of the possible screens you can share?
It does, and it's not coming up.
No.
the image that I wanted to show you is a bit odd, really. I can see everything else. Anyway, I'll just show you some targets that I've been working on just before questions. I'm keeping an eye on the time here. Oh, can you see that?
No.
Unfortunately
No? No?
You haven't
Oh.
paid your bill.
I think I know what the issue is here.
Ah.
Can you see that?
Ah, yes.
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 Okay. Yeah. Right. So you've no doubt heard of RSOP, the nova that's gone into outburst. I've been following this since August and seeing some quite distinct changes. This one was on the 16th of August, this one's on the 20th of August. I've got about 10 spectra of this and look at it every week. And you're seeing some quite interesting changes. I managed to image it on Friday night. It was clear here, and it's 12.5 meg at the moment. It's getting dimmer, and other people as well are doing spectroscopy on it, but it all depends on who's got a clear night and where they are. But lots of photometry is being done, and this is all being done by amateurs. You can see that this peak here, this is the H alpha line, by the way, and it's still emitting very strong. But this has disappeared now, and these absorption lines all along here have all disappeared. And when I had a quick look at the downloaded spectrum, and I managed to get 10, and I've yet to do the data reduction, all this looked there was a sort of peak there, and all this has gone smoothed out. This has all disappeared and smoothed out. And that's RSOP. Now, what else can I show you? Can you? No, you can't see that. If I oh, can you see that?
Yeah.
Yep.
Right. This is by Professor Steve Shaw, a schematic representation of what to expect and why. And he's written a fairly detailed article in the BE Star French newsletter, the BE Star database, where they monitor the spectral BE stars, mainly the H alpha lines. And this is a model of the nova, which has probably changed now because it's changing all the time. Now, it's complicated what is going on, and it all depends on our line of sight. But this is the only schematic I've seen of it, of what's going on. I don't pretend for one moment to understand it, and the astrophysics and the physics is changing all the time, and it's giving us a lot of information. Fortunately, we're still able to track it, but once it gets down to about 14, 15 meg, I'll probably lose it with this setup. But a word about models is this: all models are wrong, but some are useful. George E.P. Box, 1976. He was a British statistician. So what he's saying is that, yeah, you can come up with a model, and in a month's time, one of the parameters will change, and you'll have to keep changing and updating the model, as we do in astronomy all the time, as more and more information comes in about objects that we're looking at. The deeper and deeper we look, the greater the resolution we look at these objects, more questions and answers come up. So talking of which, any questions?
Yeah, I'll start off, I think, by asking you, I mean, to me, they look like massive barcodes. Yeah, you can look at those and you can say, oh, you know, here's the H beta, here's the H alpha. You know, how on earth do you remember, you know, is it experience, practice? How did you sort of start sorting out what the lines were?
Because they're calibrated.
If you take the screen sharing off, Jack, we might be able to see that better.
Yeah. Stop share. Yeah.
Yep. Okay. Now talk and hold that up.
Right. We have to take calibrations of all of the lines. That's why we know what's what. There's the H alpha line down there. If I can just point to that.
Yeah.
That's taken through a colour DSLR camera, not CCD. And I've actually got a 7-foot spectral strip here that I did when I first started out. Just grab it for you. Call it my party piece.
I think this was the one you brought to the club once, wasn't it?
Oh yeah, there you go. Yeah, I did this with a DSLR. It's about 7 foot long.
And is that a photographic film, or is that the data captured and then printed out?
It's digital on the DSL. So this is the heart of the spectrograph, the grating. I'm just going to try and take it out of its cover, if I can remember. Oh yeah, if I can remember how to do it. That's the 1800 grating. That's the next one down. Yeah, you can see that.
Right. Yeah. You can see the spectral colours reflecting.
Yeah. Okay. So these come in at €552 each. Ouch. Wow. And I'm just going to put it back in its box now, out the way safely. You don't want to be dropping that at 2 o'clock in the morning. And there's 6 of these gratings from we've got the 150, the 300, the 600, 1200, 1800, and the 2400, which is loaded into the spectrograph at the moment. It's a very versatile piece of kit. And it means you can look at all different, you can look at low resolution and at high resolution.
Yeah, those numbers you're quoting, are they lines per millimeter or?
Yeah, lines per millimeter.
Yeah.
Everything is in metric.
Do you do any work like this, Paul, or is this all new to you?
No. I mean, I can remember when I was studying maths and physics, looking at spectroscopy, and as part of physics practicals, doing sort of spectra, looking through spectroscopes, moving the angles to see various lines of different chemicals that were being burnt, to see the different colors and things. But it's just been interesting to see, you know, from the diffraction grating, and then you obviously, Jack, then have to sort of move along to focus at what particular part of the spectrum you're looking at to pick up the data. And but I've always been interested in it, because I remember way back when I was doing my A-level physics, learning about the Balmer lines in the hydrogen spectrum and things like that. So and what I was interested in was you had a little slide up on our webpage, and you talk about all the different types of information that you can actually get out of a spectrum, with all the sort of magnetic field or magnetic information, as chemical composition and everything. It was just it's quite incredible, really.
It's absolutely amazing. I'm going to show you the setup in a moment. It's fascinating what you can get out of it, and about 80% of what we know about the universe comes through spectroscopy, and we just get a fantastic amount of information. But this is we're looking in the optical here, which is 400 to 700 nanometers, but we've got all the other wavelengths. We've got the near infrared, and I'm getting an infrared camera, and I'm going to start experimenting with that to see what that will give. And that's got all sorts of uses. And then we go down to the other end, into the blue, into the ultraviolet, gamma and X-ray regions, and all these, or most of these objects emit in those regions of the electromagnetic spectrum. Like you've got X-ray satellites up there, gamma ray satellites, but the spectroscopy discussion group that I belong to, which is mainly American run, one of the guys reckons that there's next to nothing going on in spectroscopy in the ultraviolet. Can you believe that? But I don't know, or can't get an ultraviolet camera, to an ultraviolet sensitive camera to hook on the end of that. There probably are ones about, but it's an area that has apparently heat, according to them. It's not been looked into spectroscopically.
Do you think that's driven by, with the expansion of the universe, everything's moving towards the red with the red shift, so people have focused more going in that direction down the spectrum rather than the blue end?
It's not about the red or the blue shift of the object. It's about multi-wavelength imaging and what you can see at these different wavelengths. I'm sure you've seen a picture of various objects taken at multi-wavelengths, and it's now known as multi-wavelength astronomy. You've got to have a detector that can see in the infrared and the ultraviolet and the gamma and the X-ray, and you can compare the different types of images that are being emitted. One of the guys was talking about an active yesterday's Antique Telescope Society. They're all retired engineers that work for NASA or were involved in professionally as engineers that were setting up equipment. One guy was saying he was setting up this moving spectrograph on the Ascension Islands for the US military to look at certain things and bits and pieces. It was all quite fascinating stuff, and it was the type of spectrograph that I'd never heard of before. And yeah, it's got all sorts of applications. And the more you look into these objects, and the more data you acquire, the more questions and answers come up. And I showed you, I wanted to show you a star called Pi Aquarii, but that didn't come up. Targets of interest at the moment, here we have a list. So we've got RSOP, which is ongoing, but probably not for much longer. 28 Tauri, Plione in the Pleiades. Pi Aquarii and Zeta Tauri are at the moment objects of interest that I'm doing for a German database. there's a whole international amateur collaboration going on here, and I'm looking specifically in the H alpha line. Now with the Americans, they're looking at flare stars, stars like A.D. Leonis, B.Y. Draconis, V.L. Lac, right, that's up at the moment. These tend to be red dwarfs, red M-type stars. They're very cool and they're low emitters. And if it's clear tonight, I'm going to have a quick look at VL Lac. It's 10th magnitude. I just need to get a decent star chart. Hopefully it's near a bright star and I can lock onto that and just see what I can get. But they reckon that you stand a greater chance of seeing a flare event, which is a big broadening of the hydrogen Balmer lines. I don't know the mechanism which causes this to happen, but and we're not sure about the periodicity of the flare event. In other words, you've got to stare at that object all night, get 60 spectra looking at, and the flare events can be short, 10 minutes or something like that. And you might get one a night, you might be lucky and get 20 a night. So you get 60 spectra, and then you've got to process them, examine them individually to see if there's any difference. Fortunately, they have a processing pipeline where you can feed all that into, but they're not well studied because nobody gets years of telescope time to look at these objects unless you're a group of amateurs that say, hey, we want to have a look at this. Yes, professionals have looked at these objects, but only for short periods of time. They'll only get a few nights on the big telescopes to look at it, and that's it. So I'll just show you what they call the rig. I've got to reset this afterwards back on the H alpha line for tonight. I hope you can see this clearly. That's the spectrograph there, and that was the micrometer that I was turning, and that's a Paramount MX, and this is a C14. 14-inch Celestron C14. You need a big telescope with a lot of aperture because it's actually the light that you are interested in. This is not planetary imaging, and yes, the telescope has to be collimated, but it isn't important if it's not that well collimated, as long as you're getting the light onto the CCD. That's the science camera there. The Attic 460 monochrome, and there's the finder telescope that enables you to see the target, and that's I don't know if you can see that. That's a 4-inch refractor attached to the C14, and that is a moonlight focuser. And these are the control boxes down here, right? Now what we've got here, we've got the calibration module. I don't know if you can see that. That enables you to take calibration images, and that enables you to take flats images. And then it's actually an interface on the computer. I can operate this remotely. I have downloaded the computer interface. That's the moonlight control for operating the focus of the telescope, and the collimating lens of the spectrograph. I don't know if you can. I don't know if you can see that. it's motorized, and there's a belt that adjusts the collimating lens, because the spectrograph is inherently unstable to temperature, and the lens goes out of focus. And when I say the lens goes out of focus, it doesn't move. It's the way it's designed. So I actually built this this attachment here, and by pressing those buttons, I can rotate the collimating lens in and out, and that determines the resolution of the spectrum that you're going to get. And if that goes out of focus during a run of 10 spectra, that would affect the science, that would affect the resolution of the spectrograph. That's my book, by the way, published in 2010. And it's those when I was doing photographic spectra from London, Spectrographic Atlas of Bright Stars, published by Springer. Took me about 2 years to write and 10 years of imaging, pushing a Dobsonian around London skies, looking star hopping from sort of bright star to bright star. I expect it's no longer like that anymore in London, because of the light pollution just gets worse and worse. So there you have it.
Yeah,
And
that's a complicated setup with a lot of cables and feed cables and control cables and
yeah, and 3 computers. One computer runs the telescope mount,
yeah,
and PhD2 guiding. The other computer downloads the spectrums from the science camera, and another little computer down there. There's another screen up here which you can't see. I'm actually looking at 3 screens. I'm looking at 2 screens here because I can interchange with an iGeek KVM switch. But the Finder telescope over there is connected up to a different screen. So I'm just sitting here looking at that target all the time through the 4-inch refractor. I can also look at it visually as well with the flip mirror. So that finds the target. And through experience and years of doing this and collaboration with other people, you get to know the object, and you know if you're on the right target. Like, for example, Plione in the Seven Sisters 28 Tauri, it's in a field of a group of stars, and I happen to know there's 2 stars near each other. It's the dimmer of the 2 stars, and I know that through experience. And what you do is you take a quick spectrum, and it shows a double hydrogen alpha emission line, and you know that that's the correct star, because if you're on the other star, it's going to show a different spectrum, and that all comes with experience.
Wow, you're an extremely talented person, Jack. I mean, I would be at about the 0.5% level of understanding of what you've been up to, if that makes sense.
Well, yeah, it does, because it's a very steep learning curve, and I'm still learning, and I don't understand much, that much. I mean, and when we have this spectroscopy discussion group with these NASA engineers, and we've got 2 professors and a couple of PhD doctors of astronomy advising us what to look at. One's an emeritus professor of astronomy, and another guy who was a software engineer really does complicate things, and it's been argued that at our level, at the amateur level, for the likes of us, what we're doing, we don't need all this complicated software and able to look at 18th magnitude objects, which you can at lower resolution, but not with this. About 13. That's the limit with something like that, because the higher the resolution you're looking at, the lower the magnitude you're able to do. With the lower resolution spectrographs, you can go deeper in magnitude, but there's a caveat, there's a compromise. You're not going to see the effects we're looking for in, say, for example, a 10th magnitude flare star like EV LAC at low resolution. They say the hydrogen Balmer line, the H beta line will give you the best chance of seeing that flare effect, but they can only see that at low resolution. They may pick something up, but boy, is it tough to confirm it. Whereas I can load the 1800 rating because we've tried to see which rating works best at, at 5 minutes exposure, which rating is going to give you the optimum resolution, and it turns out to be the 1800 for these type of stars.
Wow.
And they're seasonal. Like we finished AD Leonis, that's gone. We finished BY Draconis. Now they're banging on about VL LAC. Some of them have already started, and they've created a database so we can upload all our data.
Okay, well, taking this from a really basic level, if somebody wanted to get started in this area, what would be the best advice? How would they, what's the best thing to get started? What equipment would they need? What sort of outlay would they be looking at? And what sort of results do you think they would obtain? A lot of questions.
Right, well, you can go on to forums, astronomical, Group SCIO, Astronomical Spectroscopy, which is Ken Harrison. He's in Australia. He runs the forum, and you've got beginners on there. So what people start off with is the star analyzer, which is a low resolution filter. It's 1¼ inch, and it screws into your camera, and you can start taking low resolution. So the star analyzer comes in at about £100. Then you've got the camera, probably a QHY would work well, but they stopped making CCD cameras. They're now experimenting with CMOS for spectroscopy. Most people are running CCD cameras, and that's another debate in itself. And there is a guy in America doing experiments with CMOS cameras, comparing them to CCD, and it's just a matter of finding the best CMOS camera to suit for spectroscopy for a specific application, which is what this is. And so then you've got the telescope. Well, with regard to the telescope, you need a big aperture telescope to get the light. I wouldn't recommend a C8 or a 9.25. I would go minimum for a C11, which is what I've got next door in observatory number 2. That's for viewing, and I started off using the C11 when I first started doing this. That's the minimum because it's all about getting the light, but you do need a good mount, and I have to say that Takahashi mounts, astrophysics mounts, paramounts, and the Americans use the plane wave mounts, which are out azimuth, that's German equatorial, but the plane waves are second mortgage job is they're they're very good, and that's what they use over there because they can afford to do it. But this is American, Paramount, and so is the telescope, Celestron. And for what I do, they serve me very well. But you can use like an EQ5 or an EQ6 mount to start off with, and if you like it, you can start moving up the ladder by buying a higher resolution spectrograph, and then you're getting into slit spectroscopy, and yeah, it can take years and years. I mean, this is 2013 this observatory started. Now yeah, 7, 8 years, and it's gone through a lot of evolution over the time. Computers have broken and failed and been thrown out. I've got the bits of other computers, PCs, running on Windows that have just failed because they're working out here through all the seasons, and I think the winter's the worst time. I think the biggest thing about having computers outside in an observatory is the damp. They do not like the damp, and eventually they will break down, and you just, I've got a guy up the road with a computer shop that's very good. I just read this one, the science camera computer broke down a few weeks ago. So I'm now running an HP Pro Intel Core i3 processor, desktop PC, and I got him to transfer the SSD hard drive, which is something like 500 gigabyte, half a terabyte, into this. But you don't hold any images on the computer here. It's all done with memory sticks, or if you want to be expensive, use a external NAS drive inside the house, and you can just dump it all onto there. But I just use a memory stick at the back here. All the data comes through there, so that in the event of a computer going down, you haven't got to take the hard drive out, because there's no data on the hard drive. Now, just a sort of a word about the computers. I used to run all the programs on one computer, and it's very easy to make a mistake. And if the SkyX goes down and it stops guiding, you've got to close down the whole operation. Whereas if find the telescope, something goes wrong on that, it doesn't matter, because you can see the object on the SkyX screen. And there's been the subject of some debate, but I have it on very good advice from people in America that these programs do not work well together. Or you have 3, 4, 5 programs all running on the same computer, you get what we call a conflict of software, and something crashes, and it can take 20 minutes, half an hour sometimes to get it up and running again, because the cameras are cooled and you've got to work at the same temperature. So you've lost half an hour of observing time.
I would say that probably from what you've described in terms of equipment, the computers are actually quite cheap in comparison.
The computers are quite cheap as in comparison.
Well, to the telescope and the gear that you've got there.
This one was £75.
Oh, as much as that. Jack, you just
so it's quite fast. Yeah. And I said to the guy, are you gonna put me in an i5 processor instead of the i3? And he said, you won't notice the difference.
Well, that's been a terrific tour of your observatory there, and great insight into what you're doing with the spectroscopy. And I know the club's got a camera which people could borrow, but I don't think we've quite got the large enough telescope that we could attach to it. But I guess that if you were doing observations of our sun, perhaps you could get away with a slightly smaller telescope. So that could possibly be a way there. So,
well, you can't really do observations of the sun because it's not safe.
No.
It's safe. You can actually take that spectrograph out and point it directly at the sun, and it's safe with the highest resolution. But you can't do direct observations of the sun by looking at it directly. I can do it, but I'm not pointing at the sun. I'm pointing at a different area of sky.
Yeah. That's obviously because of the huge difference in magnitude between the stars that you're looking at night and the sun during the day.
Yeah,
very big difference.
yeah, and the distance. I mean, I think it's minus 26.5 magnitude the sun. Yeah, we're looking at anything from 1st to 12th mag.
Fabulous. Do you have any more questions there, Paul?
No, just to say it's been fascinating to get an insight into, you know, what happens and how you go about it, and just the amount of data that can actually come piling in. And there's a lot of it, and it obviously would take a lot of time to analyze and understand. So it's been fascinating. Thank you very much indeed.
It all goes into the French or German or American databases, and as what's called a data mine. And what that means is a professional astronomer can pull it out if they want to look at something.
Okay, well, I think we'll wind up at this point.
Yes.
Then, and say a very big thank you to you, Jack.
Been a pleasure.
Well, I would say that we've been privileged to see what you've been up to and learned a lot. And I'm pretty sure that once word gets around, there are going to be quite a few people who are going to regret not having been here live, but will be very pleased that we've recorded it and they'll be able to look at it later on. So on behalf of HAG, can I say thank you very much indeed, Jack, and all the best with your future observations. So with that, I'll say
thank you very much. It's been a pleasure.
Okay, thank you very much, and I'll say goodbye to everybody, and we'll see you at our next meeting. So bye for now.
Bye-bye.
Bye-bye.